Hey guys, it's Mr. Sheelan here. This is going to be basically the walkthrough video on, if you missed this in class, how to properly draw field lines for magnetic fields. And this is also going to tie into with electric fields a little bit. We didn't really practice, at all practice drawing field lines for electric fields, but we're going to practice this when it comes to magnetic fields. So before we get going, it's just an important thing to I guess look at and to practice is kind of looking at and trying to tie it with electric fields. We're going to practice a bit of electric fields, but only just super duper simply. So what I want to do is once you get out a piece of paper, scratch a piece of paper, it can be computer paper, it can be loose leaf, doesn't matter to me, man. But let's get out a piece of paper, okay, and practice along with me. So remember, electric field lines are the lines in which are the lines that depict the three-dimensional space around a particular charged object and how the space moves to or from the object depending on its charge. And so remember, when we were working with positive charges, we were saying that positive charges move away. Okay, these move away from everything. Negative charges take in. Okay, and we saw that when we were talking about, the like charges attract, like charges repel. Like charges repel, opposites attract. This is why, because positive, for the most part, as far as we define it, positive moves the force outward, negative moves the force inward. So these just naturally are drawn towards one another. Whereas positive to positive, they're both pushing outwards, and so that's where you're going to see that kind of repulsion between them. So the way that we draw these are actually not too far from what I just drew out here as examples. But to show you properly how it is, let's draw this box. Okay, and in this box we're going to have a positively charged particle. Okay, now when we draw the field lines around here, in this case it's electric field lines, there's some rules that we have to follow. So one of those rules has to be that the lines point, and I'll put these are rules. So the lines point in the direction from, or the lines point outwards, that's one word, outwards for positive, inwards for negative. Okay. Another rule that we have to follow, lines go to the edge of the camera. Okay. A third one, lines never cross. Okay. And then where there's more or higher, we'll say charge. This includes with like magnets too. The higher the charge, the more lines we draw. Okay, which also just tacks on there, the closer the arrows, the higher the force. Okay, now these are generic rules, and number one really is specifically just for electric field lines. We're going to alter it to tweak it a little bit to make it work for magnetism, but it's virtually the same thing. It's just we have to understand magnetism's a little bit different in a particular way, and we'll get to why. But what I want to focus on, and the reason why I want to focus on electric field lines, is because we're essentially separating the negative and the positive elements. And here, hold on one second. We're separating the positive and negative positions, and we're going to practice seeing what positive field lines look like, what negative fields look like, so that we kind of remember, so that we can remember how they're going to work for magnets. So, give me a second here. Okie doke. Okay, so when we draw these are, remember, we're drawing the field lines, okay, which is virtually just like what we drew up here. We got to follow these rules. So follow with me. You've made the box, you put the positive particle in. We're going to draw the field lines for the single positive particle. Okay, and it's going to look something like this. Now, it's not terribly precise, but again, the things that we have to get right, are the directions that the forces will move, how the field will bend around these objects. We have to fill up the space, the little canvas, the little box here, and we have to make sure the lines never cross. Okay, so that's the positive. Let's try a negative. Okay. So go ahead and give it a negative a go. And here's what we should be looking at. We should be looking at, oops, that's a little off. So what I'm going to do is I'm actually going to first just draw the lines. No arrows, just the lines, and I'll show you why. And this will be true for magnets as well, by the way. And I'll just fill in these spaces because we can. So I'm going to put the arrows right here, because remember, for negative, it's going to go towards the negative. Now, I'm putting the arrows kind of in the center of these lines, near the center. And they're not all bunched around the circle. Okay, and the reason for that is because if I were to draw a negative sign here, and if I were to do the same thing over here, let's say I'm filling up my canvas, okay. All right, well, let's draw those arrows. Now maybe this one isn't so bad, but what you notice here is that all the arrows are kind of scrunched together. They're smacked together. They're really lumped hard. You know, it's very hard to find the distinct arrows. Where over here, it's very easy to find the distinct arrows. So here's a pro tip. When we draw the field lines for negatively charged particles, it's always easier just to draw them, you know, where there's space and not all the way at the end. So don't do this. Do this. Okay, so this is how we draw the field lines in a little canvas, little spots here when it comes to the positive charges and it comes to negative charges. Okay, and we followed all these rules here. So let's go ahead and then give this a go by doing this. We're going to show the field line here for positive charge and a negative charge. Okay, so, and we're going to say that this is our canvas here. So go ahead, draw that. So the task I have is, okay, we'll draw the field lines between these two. Okay, and here's what we should see. We should see this. Really, I should be putting that there. Now remember, these curl specifically because the positive charge just wants to move away from the positive charge, right? Like everything's just moving in every direction away from positive charge. And what that like inevitably is going to do is it's going to make the field lines bend towards the negative sign here. Okay, and this is what we should see. We should see, again, from positive to negative, we're showing that curl, that the force moving towards that negative guy away from the positive guy. And there's this straight attractive force in the middle. Okay, so that's the field lines for positive and negative. Okay, they attract to one another. So what would it look like if we have positive and positive? Well, when we have positive to positive, this is what we would see. Is that, again, this is our canvas here. They're going to repel one another. So again, they're going to move in all directions, but almost more so. They're going to bend almost more so away from one another. Okay. Now, because remember, at this position, it wants to move away from this, but it can't all that well because of this guy. Okay. And so what we see is this. We see these field lines, this force trying to move the best it possibly can away from either charge. And so there's this gap here, this gap where there's really nothing there due to this repulsion. Okay, and roughly speaking, we'd see literally the same thing if we had negative to negative. Okay, only it would just basically the arrows would be backwards. So if we had a negative here, what we would see is this. We would see everything wants to come in towards the negative sign here. And the space wants to come in towards both of them, but it kind of has to choose. It has to choose which one it wants to go to. Okay, it has to kind of choose, so it leaves this gap, almost like a repulsive gap that we see just like up here. Okay, when we see the arrows moving this way, the field wants to move towards the negative. Okay, now again, this is for electric field lines. But really, this is no different from the magnetic field lines that we're going to draw. And and again, this is why we're going through the electrical field lines, so we can then understand a little bit better how magnetic field lines will look like put together. So again, these rules are super important when we're working with magnets, and are pretty much, we're doing the same thing that we just practiced here with electrical fields. Just it's going to be, instead of having two separate positive and negative entities, now we're going to have an entity that has both a negative and a charged end, which is going to make things a little bit more interesting. So the rules that we're going to follow then for magnetism, okay. So the rules for magnetism, again, are pretty much the same. Oops. I'm going to write pretty much the same, except for number one. And number one's going to actually change from the lines pointing the direction away from positive towards the negative. We're just going to tweak it a little bit. It's just going to be the lines point in the direction from north to south. And north to south on a magnet, because remember, on a bar magnet, and specifically on a bar magnet, we have a north end and we have a south end. Okay? Basically, we have a positive end, we have a negative end. Okay? Roughly speaking is what it's saying here. So if you notice, if we got a negative or positive end here, negative end here, really the direction or the rule is the same. It's just the language has been changed a bit to fit how bar magnets work and just how magnets in general work, because it even works with the little disc magnet. So this would be a disc magnet on its side, or here's what this is the same magnet right here, just looking at its face. Is that like pretty much this is the north here, and then the south is on this face, and so everything moves towards that south. Okay. So anyway, I'm getting ahead of myself here. So when we're looking at, oh my goodness, if I can get a, so when we're looking at magnets, when we're drawing magnets, magnetic field lines, okay, have a better representation here. When we're drawing magnetic field lines, we're pretty much, again, drawing the same rules. The lines don't cross over. You'll have, more lines where there's a stronger force, and you are going from north to south. So using this bar magnet here as an example, it would look like this. So again, going from north to south. And if you want to, I like doing this. I like putting a line in the middle here, just because usually like the north end they're colored, while like usually with red, while south is not. just draw one to kind of have a better visual representation here. So the field lines going from north to south are going to be the same. We are going to draw them from north to south, just like this. Because what's happening is that the field, the space around these guys, yeah, that could have been better. Space around these guys are magnetically being affected in this way. And how we know that is because we can actually use iron filings to show this shape. Okay. And again, the force is going to move from north to south. I'm sure we could actually toss in a couple in there as well, just to fill in the space. Okay. But again, they don't ever cross. Now that guy's getting pretty close to crossing, but they're always moving from north to south, just like what we saw here with our almost exactly the same that we see it here in our positive to negative charged particles. The only difference here is that very similar to a current in what's happening internally, because I'm sure you're wondering, like, okay, well, why inside? Why doesn't it move from north to south inside the metal? Well, you could almost think that magnetism works in a metal like it does with electricity. It has to come in from one end and go out another. So if you were to take a bar magnet here and you're able to see how the energy is moving through, so this is a side view of the magnet's actually going to be moving from a what you could say is a high potential to a low potential. So the high potential is going to move, so this is north end, this is south end. It's moving through the magnet like this, and it's just recycling over and over and over and over again, right? And that's kind of that's what magnetism is. It's this constant cycle, changing of poles, changing of potential, I should say, change of magnetic potential, of energy potential on one end to the other. What kind of example? A pump like a, man, it's really hard to say what the difference would be that you may have seen before. But again, all I can say is that it's a circular, cyclical kind of pump that you go from high potential to low potential. Same way that a gas wants to go from high potential to low potential. Same way water wants to diffuse from high water potential to low water potential. In fact, that's actually a good example. That if you've ever wondered how trees get water up to the leaves, it's because there's a lot of water there's a lot of water that's in the ground, relatively speaking. There's not a lot of water that's up in the trees, and so more or less, and there's air that's let out at the top of the trees through the stomatas. And roughly speaking, super generally speaking, it almost creates kind of a vacuum. And the water is going to go from a high potential to a low potential, and it's going to defy gravity and get sucked up the tree like a straw. That's what you do with straws. It goes from a high potential to low potential. You're creating an artificial vacuum, more or less. So anyway, you can almost think of mechanically how that works with the energy within a magnet. High potential, low potential, and it's cyclical. And so when we look on the outside of a magnet, because it's not traveling through this way, it's traveling this way inside the magnet, when that energy is outside the magnet, it creates that field to then go from high potential to low potential, just cycle this way. And it just has to physically move into space because it's again, energy has to find a particular track. It just can't randomly just distribute itself, right? Like it finds a track in order to go from the north to the south. Okay, so what I want you to do then is then on your own, kind of using this as a gauge, using images on just Google, on a PowerPoint that I'll send you guys. What I want you to do is I want you to do the field lines that we drew for this guy up here. I want you to draw the field lines for the magnet right here. So here we have opposites attracting, but you still have the poles over here. Okay, so draw the field lines for that. Here we have south to south. want you to draw it going from south to south, and I want you to show going from north to north down here and show what that would look like, okay? So make sure that the arrows are pointing in the right directions. Make sure the lines don't cross. Make sure you're going from north to south, not south to north. High potential to low potential. And then this is going to be a good little exercise before we move on to actually showing this in a little lab. And if you're absent or have been absent, I will try my best to come up with something for you guys to work on at home. Anyway, so that is it. That's all I have for you guys. So here's a good way to practice when it comes to magnetic field lines. And yeah, if you have any questions for me, make sure you reach out. If not, I'll see you in the next one.